This is the lecture recording for the relationship between free energy change and the reaction quotient, as well as the equilibrium constant. It's essentially the combination of chapter 19 material and chapter 15 material. And so the idea is that if you have an equilibrium mixture, you have some reactants A and B reacting to make C and D, the equilibrium expression as well as the reaction quotient is given by the product of the products raised to their stoichiometric factors divided by the reactants raised to their stoichiometric factors. And the idea is that if Q is less than K, that is, the reaction quotient is smaller than the equilibrium constant, the system's not at equilibrium and there's not enough products, so the reaction will shift to the right to make more products. If Q is equal to K, the system is at equilibrium and no further change will occur, even though the reaction is happening in both directions but at the same rate. If Q is greater than K, that means the system is too heavy in terms of products. There's too many products, and so the reaction will back react from products to make reactants until Q equals K. This relates to free energy change in the following way. There are two factors, two ways we can talk about free energy change, delta G and delta G0. Delta G0 represents the energy change, free energy change going from completely reactants to completely products. Delta G is the free energy change going from whatever state you're in to the equilibrium state. And Q is the reaction quotient, of course. So Q represents the current state of the system. So Q is basically telling you where you are right now. Delta G determines if the reaction is in its current state is going to be spontaneous in one direction or the other direction. And delta G0 determines whether overall a reaction is product favored or reactant favored. This will make more sense as we go on. If delta G, not as opposed to delta G0, as delta G is less than 0, that means the reaction is spontaneous in the forward direction. That is same as before. If delta G is negative, the reaction will go forward. If delta G is equal to 0, the reaction is at equilibrium. If delta G is greater than 0, that means that there's too many products and the reaction will shift in the reverse direction. So these relate to the Q and K things. This relates to Q being less than K. This represents Q equal to K, and this represents Q greater than K. So those are the same, these mean the same thing. Now, if you have delta G0, that represents going completely from reactants completely to products. So if delta G is negative, the reaction is product favored, meaning that an equilibrium system will be mostly products. If delta G is greater than 0, it's reactant favored, meaning an equilibrium system will be mostly reactants. And if it's equal to 0, it's neither reactant favored nor product favored. That's an extra dot right there. No additional fee. All right, so let's look at the mathematical equation that connects these. Delta G, that is the change between the current state and equilibrium, is equal to the delta G0 value, which can be calculated as we've calculated before, plus the gas constant R times the temperature in Kelvin times the natural log of Q. And so we're going to look at an example here, and we're going to use the thermodynamic data here. Delta G is a formation. And we want to know what is delta G for this particular system at 298.15 Kelvin if all of the gases have that pressure. So we're doing this in terms of Kp, or Q in terms of pressures. And so the two things we need to do is we need to determine Q, and we need to determine delta G0. Let's do delta G0 first. So delta G0 is going to equal the free energies of formation of the products minus the reactants. So it's going to be 2 times it for nitrogen dioxide, so it's 2 times 51.3, minus 2 times the free energy of formation for NO, which is 86.6, plus 0. The 0 is for the oxygen. It has a free energy of formation of 0. That comes out to be minus 70.6 kilojoules. So then, that's delta G, we know that. Now let's figure out Q. For Q, we need to convert everything into atmospheres. So the pressure, and remember all of the gases have that pressure, are equal to 16.91 millimeters of mercury times 1 atmosphere over 760 millimeters of mercury. that equals 0.02225 atmospheres. So Q is going to equal the pressure of NO2 squared over the pressure of NO squared times the pressure of O2. And because all of these are the same, it's going to be 0.02225 atmospheres squared over 0.02225 atmospheres cubed, because there's 2 here and 1 there, which is going to equal 1 over 0.02225 atmospheres, which equals 44.94. So that's Q. So then we can determine delta G. So delta G is going to equal delta G0 minus 70.6 kilojoules plus R 8.314 kilojoules, times 10 to the minus 3 kilojoules per Kelvin mole times the temperature, 298.15, times the natural log of Q, which is 44.94. And when we do that, we come up with minus 70.6 kilojoules plus 9.43 kilojoules which comes out to minus 61.2 kilojoules. So notice that the fact that Q is greater than 1, the fact that Q is never mind. Okay. The next thing we're going to do is we're going to use this to determine the equilibrium constant K. And the way this works is this is the relationship between delta G0 and K. And the reason this works is that we have this overall equation, and at equilibrium delta G is equal to 0. And so 0 equals delta G0 plus RT ln Q. So you can solve that by moving the delta G off to the other side. And so you end up with 2 equations. You end up with this equation, or this equation, which are really the same equation, just written 2 different ways. And we know delta G0 is minus 70.6. So basically to find K is going to equal e to the minus 70.6 kilojoules divided by 8.314 times 10 to the minus 3 kilojoules per Kelvin times the temperature, which is going to be 298.15 Kelvin, and we just basically solve that. Which gives us e to the minus 28.48 which gives an equilibrium constant of 4.28 times 10 to the minus 13. And that's how that works. You can also do the opposite calculation. That is, if you know the equilibrium constant, you can calculate delta G. And so in this case, we'll use this version here. So delta G0, we'll rearrange this a bit. Delta G0 equals minus RT ln K. And so for this reaction, we know the equilibrium constant is 1.11 times 10 to the 6th. And so we can figure out delta G0 for the reaction, and then figure out what's the free energy change if you have 1.67 moles of this reactant reacting. Oh, by the way, there's a missing arrow here. It didn't copy in when I did this. So delta G0 is going to equal minus R, 8.314 times 10 to the minus 3 kilojoules per Kelvin, times the temperature, which is not given. We'll assume it's 298 Kelvin, times the natural log of K, so it's natural log of 1.11 times 10 to the 6th. I'm going to calculate that. And that equals minus 34.49 kilojoules. And that's for that reaction as written. And so then we want to know what's the free energy change if 1.67 moles reacts. So what we have is we have 1.67 moles of Fe2O3 times negative 34.49 kilojoules per 3 moles of that. So this delta G is for this reaction as written, which is for 3 moles reacting. So it's per 3 moles of Fe2O3. And that gives minus, get back there, minus 19.2 kilojoules. Okay, now let's look at this graphically. Let's get rid of my minus one I mistakenly wrote there. Alright, so now this is a plot of free energy, that is G, for the reaction coordinate. So this is 100% reactants on the left. This is 100% products on the right. And so the difference from going from 100% product, reactants to 100% products, that's delta G0. And so this reaction is delta G0 is negative because it's going down, so it is product favored. Now the free energy is actually goes down below the energy of the products. And so the lowest energy is actually not where you have 100% reactants or 100% products. It's somewhere in between. And the equilibrium mixture is the low point on the free energy, the G curve. And notice that this G curve lies to the right of the center point, which is why it's reactant favored. You have more here. And so delta G, as opposed to delta G0, will always be in the direction of going towards that. So if you have a situation where you have that composition of reactants and products, it will react in that direction. If you have this composition here, it will react in that direction. And so when you're at the state, so and this relates to Q greater than K, and this relates to Q less than K. A system that was more heavily reactant favored, or more product favored, so here we have products, here we have reactants, here we have free energy. A system that was much, much more highly product favored would be, well, when you get near the edge, when you get near the edge, the pen thinks for itself. It's not acceptable. So a system that is very heavily product favored will be something like this. So the equilibrium mixture lies way towards the product side. Okay, now the converse of that is a system that is reactant favored. And here, delta G0 is positive because you go from reactants, pure reactants to pure products. That's reactant favored because it's going energetically uphill. And now the curve of free energy versus the extent of the reaction lies to the right of the 50-50 mixture. So that's why it's reactant favored. And if you have fewer products than that, it'll go energetically downhill this way. And if you have more reactants than more products than that, it'll go energetically down that way. So of course the reaction always goes energetically downhill towards equilibrium. A reaction that's very, very heavily favored, reactant favored as opposed to product favored, would look like this. It would go down just a little bit. The low point would be almost all reactants. So a reaction that doesn't want to go hardly at all is like that. The equilibrium mixture lies way, way towards the reactant side. So the question then is, can a chemical system have a positive value of delta G, 0, yet still be favored to react in the forward direction? So you know that a positive value of delta G 0 is a disfavored reaction. It's disfavored to make products, so it's reactant favored. And so the question is, can it react at all in the forward direction, or is the fact that it's disfavored means it doesn't react in the forward direction? And the answer is yes, it can. And so what happens is, I'm going to use this one here, that's a little too broad. Let's say you have a reactant favored system that goes like that. So this is all products, that's all reactants. If you start with all reactants, it will react forward to that spot there. So maybe 10% or so of the reactants will be converted to products. And this comes into play for lots of things. So for example, insoluble salts we consider insoluble, like say silver chloride solid, it's an insoluble salt. If you mix silver ions and chloride ions, you get that precipitate. But it actually dissolves a tiny bit. It goes to make Ag plus Cl minus, and about 10 to the minus fifth moles per liter will dissolve. So that's how far forward it will go. So even highly disfavored reactions, that is highly reactant favored reactions, can still go forward a little bit and before they reach equilibrium.